Assalamu alaikum warahmatullah and good day. My name is Arif Zahiruddin bin Arnizan, and today I will be presenting my final year project entitled Production on High-Calorie Biocooks Using Oleaginous Microalgae. My supervisor for this final year project is Associate Professor Dr. Koji Iwamoto. Here is the general sequence that will be used for this presentation. We will start with the introduction, followed by the literature review, and then I will explain about the research methodology, followed by the results, and then the conclusion. In recent times, there's been an increase for the demand of energy. Due to issues such as global warming and pollution, researchers have turned to alternative sources of fuel, more specifically sustainable fuel sources. This turns to biomass, which is both an organic and sustainable source that could replace fossil fuels in the future. The sources are shown on the right, but specifically in Malaysia, the resources available is the forestry crops and the agricultural crops. The main issue right now is the energy conversion, where it is not enough to replace the current energy resources. Therefore, from here, biocoke, which is a solid and compressed biofuel. This is a promising technology that can both reduce biomass waste and can become an alternative fuel source for furnaces and so on and so forth. Moving on to the problem statement. As mentioned before, the problem is that the biocokes have a relatively lower calorie content compared to fossil fuels today. Oleaginous microalgae is a promising source of raw material for these biocokes. However, very little research has been done on these microalgae biocokes. This leads to the objectives of this research, where first it is to produce biocokes using specific strains of oleaginous microalgae as a biomass source, and second, to conduct analysis for the properties of biocoke production from oleaginous microalgae. Moving on to the research scope. In this research, the properties of the biocokes are tested. More specifically, it is the apparent density, the maximum compressive strength, the combustion test, the thermal gravimetric analysis, as well as the calorific value and heating value. These parameters are what are usually used to determine the effectiveness of the biocoke, and these data will be used in comparison with different species of oleaginous microalgae to determine which is the most suitable to become the raw material for biocokes. Again, as I've mentioned before, the main limitations in this research is limited by the availability of research analysis laboratories due to the ongoing pandemic. Now we move to the literature review. The biofuels are classified into three categories, which is the first generation, made up of edible biomasses, the second generation, which come from feedstocks, such as municipal solid wastes and lignocellulosic feedstocks, and finally, third generation, which is algal biomass, the one that this research is focusing on. Below shows the advantages and disadvantages of biofuels. I would like to draw your attention to the costs aspect, where you can see, although that it is made from renewable resources, it is very expensive, which is the main limiting factor of biofuels today. Here we move to the further definition of biocokes. Biocokes are a fuel with a high feedstock availability, meaning it can use almost any other biomass as its raw material. Low sulfur content, meaning it has low pollution rates, as well as relatively economically efficient production process. In other words, it's very easy to produce. On the right, we can see the diagram for the production of biocokes, where on the right is the piston where it exerts a pressure onto the mold. And on the left, we can see that there is a furnace which heats the entire mold. Now we move on to the definition of oleaginous microorganisms. So these are microorganisms which are able to produce more than 20% of its weight in lipid content. In terms of microalgae, these can be the ones that are used in this research are the four following below: Nanochloropsis, Aurantiochytrium, marine diatoms, and Chlorella. As you can see below, the lipid content for each of these are mentioned, where Nanochloropsis has 37 to 60%, Aurantiochytrium has 20 to 55%, and so on and so forth. This lipid content actually varies with stress-inducing conditions, such as nitrogen deprivation, carbon dioxide aeration, and these factors are the ones that will contribute to the amount of lipids within the cells which will also contribute to its heating factor or calorific value tests. Moving on to the research methodology, on the left we can see apparent density, where we measure the mass and volume immediately after biocoke production. On the right are the parameters that we should have measured. However, due to constraints of the pandemic and so on and so forth, we were unable to do so. The first parameter, maximum compressive strength, is where we use a compressive press machine to find the mechanical strength. For the TGA, the thermogravimetric analyzer, which this measures the characteristics of combustion and changes in mass. The combustion test tests the length of time of combustion under specific conditions. And finally, the calorific value uses a calorimeter to measure the value of the biocokes. So here, figure 1 shows the final oleaginous microalgae biocokes that have been achieved based for this research. Starting from the left, we have the pine sawdust, which is control, the chlorella biocoke, the nanochloropsis biocoke, the Antiochitrium biocoke, which is slightly deformed, as well as the diatom biocokes, which are divided into two, the 4% moisture and the 14% moisture. Here are the results of the measurements of the results that we have found. As you can see, the control is on the left with the rest of the oleaginous microalgae on the right. So from here we can see the respective densities, and high density means that less space is needed for a specific fuel, which is good. And high density also is an indication of a high quality solid biomass fuel, where this also shows that it has a high energy content per volume, as well as the higher the density, it has slower burning characteristics. Next, we move to the expected results. So due to the pandemic and as well as the maintenance of certain analysis machines, the analytical laboratory and other facilities were unavailable or closed. Therefore, the following data is mentioned are the expected results based on previous literature. So first is compressive strength. A lower percentage of composition of lignin within the raw material could cause low maximum compressive strength. As oleaginous microalgae are not a plant cells, they have no lignin at all, meaning to say that it is expected that they have lower compressive strength. Now this is actually shown with the Aurantiochytrium biocoke, which is actually very soft and almost malleable when touched. Now we move to the thermogravimetric analysis. The most important part is actually the lipid degradation. As you can see that there is a various amounts of lipids within each separate oleaginous microalgae. First, we can see the nanochloropsis, where the degradation of proteins lipids actually occurs at about 320 degrees Celsius. Next, for the Aurantiochytrium, it actually occurs at the second peak, which is about 500 to 600 degrees Celsius. Finally, chlorella, which occurs where the degradation of proteins or lipids, or otherwise known as devolatilization, occurs at about 140 degrees or 560 degrees. Based on the calorific value research, all the biocokes are expected to have a heating value range of about 12 to 19 megajoules per kilograms, based on the heating values of bio-oils that could be extracted from these oleaginous microalgae. For example, bio-oils made from nanochloropsis have a heating value of about 12.6 megajoule per kilogram. Next, we move to the combustion test, where although this is reliant on its density, the lipid amount of each raw material could also affect combustion's length. And again, nanochloropsis is expected to have the longest combustion time compared to all the others, with an apparent density of 1.348 grams per milliliter and a minimum average lipid content of 37%. This research shows some promise, particularly with biocokes made from nanochloropsis. However, for other biocokes, the density and also other factors may not be enough to become more energy dense and become marketable in the current market. Predicted results also rely heavily on prior research of the raw material without considering the effects of biocoke production to its properties. Other parameters such as the moisture content and their respective maximum compressive strengths must also be further researched and tested, as these parameters also severely affect the quality of the biocoke produced. And finally, the use of oleaginous microalgae could be combined with other biomasses to create a more stronger fuel source for increased marketability and effect. That's all from me. Thank you and Assalamu alaikum.